All right, what we're going to start to do is take all of this work that we've been doing factoring polynomials and connect the term factor with the term root. All right, so what we want to start doing is investigating the components of these functions, maybe they're parabolas or cubic functions or whatever they are, and figuring out what exactly it means when you find a factor and how that helps you figure out where the roots are of a function. And this probably won't be new to you. It's probably going to be something you've done in Algebra 1. So what we're going to be able to do after today's lesson is solve any quadratic polynomial using either the grouping method, which we're familiar with, or the quadratic formula, which we will be introduced to in this lesson. But again, it may be something that's review. And before we start, I'm just going to kind of begin by saying that factors and roots are directly related to each other. And factors can become roots. You can use roots to figure out what the factors might be of a function, but they're not the same thing. Okay, so factors, for example, might be like x plus 1, and a root might be x equals negative 1, right? Or maybe we have a factor that is 2x plus 3, which would lead to the root negative 3 over 2. And I'll explain how we go through that process, but it is important to distinguish between the difference between a root and a factor. All right. So what we're going to do here is describe the features of this function that we've been given, this f of x. It's a parabola, so we know that. And from our previous lesson, we could say a lot of things about this. One of the things that we could say is it should have two roots. All right, we know that just from what we did in class. Another thing that we know is that its maximum number of extrema, meaning its turning points, would be 1. Remember, parabolas either look like this or they look like this. So they're only going to have one maximum or minimum. Excuse me. All right, its y-intercept. Remember, its y-intercept is just defined by that constant. So the y-intercept is at y equals 6. And then the end behavior. This is positive. All right, so if we go to our box to remind ourselves of end behavior, we've got an even, odd, positive, negative. We're dealing with a positive even. And remember, positive even polynomials have end behaviors that look like that, right? Who cares what's going on in the middle, but on the ends, it's going up in both directions. So I would say as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x is approaching infinity as well. All right, all of this is stuff that you should know just from looking at this equation. Okay, but what you don't know yet is how to find where these roots are, and those are pretty important. So we're going to use the equation here to figure out where the roots are. Luckily for us, we know how to do this because we know how to factor. So there's really just one step that we need to add to the factoring process to find roots. Okay, but before we do that, let's just take a look at what a root is just for a second so that we can explain why we need to do what we need to do here. If I had the graph of a parabola, and I know that this parabola looks something like this. All right, something like that. What I want to do when I find my roots is find these points. And remember, those points are just coordinates on the coordinate plane, right? They have an x-coordinate and they have a y-coordinate. The interesting thing about a root, though, is that all roots have the exact same y-coordinate. Because I don't know what these x values are, but I do know that this is the point something 0. The y-coordinate is definitely 0. And over here, I have the point something in the x direction, but I'm not going up or down in the y direction, so the y-coordinate is still 0. So one thing I know about each of these coordinates, and I don't know the x-coordinate, but I do know that both of the y-coordinates are 0. So what I'm really trying to do here is figure out when is this polynomial equal to 0. So what we'll do is we'll set this thing equal to 0. Instead of writing f of x, we'll write 0 equals x squared plus 5x plus 6. Because we're trying to figure out what x values make this function have a y coordinate of 0. And so what we want to do now is we want to try to solve this thing. And there are a lot of mistakes that you may make if you try to do this without factoring. For example, you may try to subtract 6 from both sides, and then you'd have negative 6 equals x squared plus 5x. And I don't know what you would do to try to get the x alone. Maybe you'd try to divide by it on both sides. This is going to just cause you to run into more problems, right? We haven't solved for x here. We just have 2 of them now. So this would all be just counterproductive. Wouldn't help us. So what we're actually going to do is just factor. I know that if I factor this polynomial using the AM method, I'll get x plus 3 and x plus 2. I made a list of my factors of the number 6 and found the 2 that added up to 5, so 3 and 2. And so what I have now is I have a statement that says my quadratic is the same thing as this times this, because these are its factors. But if this function is ever going to equal 0, one of these must be 0. Right? If I'm going to multiply something by another thing and get 0, one of those 2 things must have been 0. So what I need to do now is set up a situation where I say, well, what if it's the x plus 3 that's 0? And if x plus 3 is 0, then what would x be? So I'd start solving this, and I'd figure out that if x plus 3 is the factor that's 0, then negative 3 must be the value of x. Meaning, if I plug in a negative 3 into this original equation, I will get 0. And I'll do the same thing with this other factor, because maybe it's the x plus 2 that's 0. And if it is, then x must equal negative 2. So what I've figured out is the places where this function is equal to 0 are when my x-coordinate is either negative 3 or negative 2. So I just figured out that that is a negative 3 and that is a negative 2 because we solved our quadratic. And all we need to do this is just factor. We just need to be good at factoring, which is something that we've been really practicing a lot. All right, so where are the roots located? The roots are located at x equals negative 3 and negative 2, and that is a fine way to write your answer. You don't need to write the coordinates. You could say that the roots are at negative 3, 0, and at negative 2, 0, but that's kind of redundant because if it's a root, we know the y-coordinates are 0, so you don't need to write the y-coordinates. You can just tell what the x-coordinates are, and that's a fine way to leave your answer. Let's try another one. This one says to determine the solutions, and above it said to determine the roots. Solutions mean the same exact thing, except they're just referring to an equation rather than a function. So they're just saying, let's not think of this as being something we would graph. Just solve x. Figure out what values of x would make this thing equal to 0. All right, so when is 2x squared minus 3x minus 1 equal to 0? Oh, not minus 1, minus 2. Well, this is going to be another difficult thing to do if we don't use factoring. So I'm going to use my factoring methods. The AM method isn't going to work. I already tried the GCF method. They don't all have a common factor. It's not a difference of squares. So we're going to run down our list of factoring methods and get all the way down to the grouping method. So I'm going to make a list of my factors of negative 4. Hopefully this is something that you've paused the video and gone ahead and done already. And I'm going to pick the 2 factors of negative 4 that add up to negative 3. So negative 4 and 1. All right, so I'm going to go straight to here. 2x squared minus 4x plus 1x minus 2. And now I'm going to group. And GCF here is 2x. And GCF here is 1. And one more time. Okay, so we factored. And now we just have to figure out, well, when would this thing be 0? Well, this would all equal 0 if this were equal to 0. That would make this 0, right? Because 0 times whatever this is would end up being 0. So let's figure out what that would be. X minus 2 equals 0. And I'll just add 2, add 2. So then in that case, x would have to be 2. So we figured out that one of the solutions is 2, because if I plug in a 2 here and here, I will get 0. But maybe it was this factor that was 0, right? Because if this were 0, this would also be 0 when I multiply it by something else. So we'll solve for that one as well. And this is going to be 2 steps, minus 1, minus 1. Now I have 2x equals negative 1. And now I'm dividing by 2. All right, so what I've learned now is that this has 2 roots, which we knew about. We knew it would have 2. And the 2 roots are, well, so the 2 solutions are 2 and negative 1/2. And if you wanted to check this, you could throw that negative 1/2 in there and evaluate, and you would get 0. So you could just say that the solutions are x equals negative 1/2. And I'm just putting that first because it's the smaller of the 2 values, and 2. All right, now before we get to class, what we're going to do is write down the quadratic formula. And there will be cases where you'll be asked to solve something like this and it won't factor. And this isn't a problem we've run into yet, but there will be times where we'll see a quadratic and it won't factor at all, so we need a tool to use. So what I want you to do before you come in tomorrow is I want you to look up the quadratic formula and put it right here in a big box. Write down what that quadratic formula is. Okay, just Google the quadratic formula and write it down. You probably will recognize it. You've probably used it before, but we're going to be using it in class, and we'll talk about it more when we get there.